Hello, this is the third part, final part of lecture 5 of linear algebra. And this part is also about diagonalization. Okay, first let me translate what we did in the previous part into the language of linear operators. And then we consider some examples. And after this, we generalize diagonalization for complex matrices, because actually we need complex matrices for the next week. We need one result about complex matrices, which we're gonna prove in this part today, which we're gonna use next week to prove one result about real symmetric matrices. So we have to consider complex matrices now. Okay, so let's start with the translation of diagonalization results about matrices into the diagonalization results for linear operators. So first, let me define what is characteristic polynomial of a linear operator. It can be done in several ways. The simplest way, probably, you can take a standard matrix of linear operator, and then you take its characteristic polynomial. This is correct, but we can do it in a more general way. We can take linear operator and we take its basis with its matrix with respect to any basis of Rn. And then you can define a characteristic polynomial of your linear operator as a characteristic polynomial of this matrix. Yeah. Here you have to justify that this definition makes sense. You have to say that this characteristic polynomial, this polynomial determinant a minus lambda I, is independent on the choice of basis. But this follows from two results we proved in the previous parts of this lecture. First result, that similar matrices has same characteristic polynomial. And second, if you take two different matrices of the same linear operators, they are similar. This was basically the result we started with this lecture. Okay, so using these results, you see that this definition makes perfect sense. If you're unhappy with this, just take standard basis of linear operator and take characteristic polynomial. Yeah, okay, this is also gonna work, but in some examples, it's easier to take non-standard basis to compute this characteristic polynomial. Okay, and using the result for matrices, we see that the eigenvalues of your linear operator T are real roots of characteristic polynomial. The proof is essentially the same as for matrices and can be derived from the similar result for matrices by this property. Okay, good. So let me give you an example. I choose some random sporadic basis of a plane of R2. Just I randomly grab these vectors, and then I define linear operator T by these two equalities. If you remember, we proved somewhere earlier in the previous lectures that linear operators uniquely determined by its values at basis vectors of the vector space. So from these results, I know that there exists linear operator T from R2 to R2 such that T of V1 is 2V1 and T of V2 is minus V2. And such linear operator is unique. So this is basically the way how I can define a linear operator. Yeah. Okay. So if you ask me what is the standard matrix of this linear operator, I don't know. I can compute, but I don't know. But with respect to this basis, its matrix is very simple. It's by definition diagonal. Yeah, this is a matrix of this linear operator with respect to this basis. Yeah, because by definition, linear operator basically what it does, it just scale vectors v1 and v2. So this means its matrix with respect to this basis is diagonal. Yeah, and then I can compute its characteristic polynomial. Basically, it's a characteristic polynomial of this matrix. Again, if I only allowed to use standard matrices, I'm gonna have to make a lot of computations in order to compute this characteristic polynomial, and the result going to be, of course, the same. Okay, now let's go to criterion for diagonalization. And first of linear operators, but first we have to define what does it mean for linear operator to be diagonalizable, which implicitly we did actually in the beginning of this lecture. So basically it means a linear operator is diagonal if its matrix with respect to some basis is diagonal. Or you can state that, restate this, say linear operator is diagonalizable if there exists a basis such that the matrix of linear operator with respect to this basis is diagonal. So this system of equalities basically means matrix of linear operator T with respect to this basis is diagonal. Yeah. Just by definition, what is the matrix of a linear operator with respect to given basis? Okay. We can prove that the following conditions are equivalent. The linear operator is diagonal, standard matrix of T is diagonalizable, linear operator is diagonalizable, standard matrix of T is diagonalizable, matrix of T with respect to any basis diagonalizable, matrix of T with respect to any basis to some basis is diagonal, or there exist n linear independent eigenvectors. All of these conditions are equivalent. Implicitly, we already proved that they're equivalent earlier in this lecture. Even when we prove this for the matrices, we implicitly use several results about linear operators. Yeah, okay. So this is very nice way how to check that the linear operator is diagonalizable. But we can say more if we know that, for example, these numbers lambda 1, lambda 2, lambda m, these are of course eigenvalues. If we know that all eigenvalues that are different, if your linear operator has n different eigenvalues, then we know from the corresponding result for matrices that the standard matrix of this linear operator is going to be diagonalizable. We proved this. This is not obvious, but we sketched the proof in the previous part, so we can use it for linear operators. If your linear operator from Rn to Rn has n distinct eigenvalues, you don't need to check anything. It's diagonalizable. Okay, good. Now we can restate the diagonalization criterion for matrices in terms of algebraic and geometric multiplicities of the eigenvalues for linear operators. But first we need to define geometric and algebraic multiplicities of eigenvalues or for any number as we did for matrices. Essentially, this is just a translation of our definition for matrices in the language of linear operators. So we have linear operator and we have some number delta, any number delta. Then geometric multiplicity of delta is just dimension of the delta eigenspace of T. Recall that we mentioned last part that delta eigenspace of T is the same as delta eigenspace of the standard matrix of T. So this is basically the same geometric multiplicity of delta of a standard matrix of T. Yeah. Okay. So we, as for matrices, we denoted by gamma T of delta. So if delta is an eigenvalue, then this space has positive dimension. This space is a kernel of the matrix standard matrix of T minus lambda times identity. So this space consists, if delta is an eigenvalue, this space consists of all eigenvalues, all eigenvectors of T with eigenvalue delta plus zero vector. So if delta is not eigenvalue, this is just the zero dimensional space. This is just a zero. So geometric multiplicity is zero. Okay. Similarly, algebraic multiplicity of delta is just the multiplicity of delta as a root of characteristic polynomial. So if delta is not a root of characteristic polynomial, then its algebraic multiplicity is zero. It's just not a root. If it's a root of characteristic polynomial, then you just look maybe it's repeated root. If it's repeated root, you just count how many times it appears in this decomposition of factorization of your characteristic polynomial into the linear parts, linear polynomials of degree 1. Yeah. Or alternatively, you can say you look for this powers lambda minus delta and take the largest power such that it divides your characteristic polynomial. Yeah. This is just multiplicity of a root of characteristic polynomial. Yeah. If delta is is its root. If delta is not its root, then algebraic multiplicity is 0. This is the same, of course, as our geometric multiplicity of delta for standard matrix of T and algebraic multiplicity of delta for the standard matrix of T. So this is just a translation from the matrices. And we mentioned, but we didn't prove, but we mentioned, very important inequality, that geometric multiplicity cannot be larger than geometric multiplicity. It can be smaller, and we saw several examples, but it cannot be larger. Okay, so using this, we can state our criterion for diagonalization. This is basically translation, almost a copy-paste, to be precise, translation for the corresponding criterion for matrices. Linear operator is diagonalizable if and only if geometric multiplicity of every eigenvalue coincide with algebraic multiplicity of this eigenvalue. And all these eigenvalues are real. I mean, all eigenvalues are real by definition for the real linear operator. All roots of characteristic polynomials are real. So if you have linear operator, you take its characteristic polynomial. First thing you check that all roots of characteristic polynomials are real. Complex root, non-real root, not diagonalizable. If all roots are real, the next thing you check geometric multiplicity of every root, and you compare it with algebraic multiplicity. If they are the same, in each case, your matrix, your linear operator is diagonalizable, or you can say its standard matrix is diagonalizable. So this condition that sum of geometric multiplicities equals n, this is the translation for the fact that all roots of characteristic polynomials are real, because sum of algebraic multiplicities is exactly n when a sum goes through all distinct eigenvalues. Okay, good. So this criterion for matrices and for linear operations often used only in one direction to prove that something is not diagonalizable. If you feel or if you know that the matrix you consider is not diagonalizable, you don't need to check all conditions of this criterion. You just need to check that only one condition fails. And this gives you what is called like abstraction for diagonalization. Abstraction for diagonalization is a condition which actually abstract your matrix to be diagonalizable. Namely, this is just immediate corollary of the previous theorem. Take an eigenvalue of A, real eigenvalue of A. If geometric multiplicity strictly less than algebraic, matrix is not diagonalizable. You just don't need to check anything else. End of game. Okay, let's consider example. You take this matrix A. You look for its eigenvalues. Eigenvalues are 1, 1, and 2. And 1 is repeated root of characteristic polynomial. So this is suspicious. If you see repeated roots, it means danger. It's a possible problem for diagonalization. So its algebraic multiplicity is 2. You compute its geometric multiplicity. How to do this? You subtract from this matrix A 1 times identity. You get a matrix 0, 1, 0, 0, 0, 0, 0, 0, 1. Rank of this matrix is 2. So by rank nullity theorem, its kernel is one-dimensional. Dimension of the kernel, it's exactly geometric multiplicity. So it is 1. So end of game. A is not diagonalizable. Algebraic multiplicity is larger, strictly larger than geometric multiplicity. Okay, let's consider one more example. Even simpler one. You take this matrix, you compute its characteristic polynomial, is just lambda times lambda minus 1 square. Again, it's this is an upper triangular matrix. Its eigenvalues is just diagonal elements, and 1 is a repeated root of characteristic polynomial. So multiplicity, algebraic multiplicity of 1 is 2. Algebraic multiplicity of 0 is 1. So 1 is a suspicious root. So if geometric multiplicity of 1 is less than 2, it's a problem. Matrix is not diagonalizable. How to check this? By definition, you subtract from A identity matrix multiplied by 1, which is identity matrix. So you get a matrix 0, 1, 0, 0, 0, 0, 0, 0, minus 1. Clearly, its rank is 2, because it has 2 linearly independent columns or 2 linearly independent rows. So the nullity of A is 1. Nullity is dimension of the kernel. So geometric multiplicity is 1 less than 2, which is algebraic multiplicity. Matrix is not diagonalizable. Okay. Okay. Yes, another way how you can reprove what we just said without using any criterion, but using the fact that similar matrices has the same characteristic polynomial and have the same eigenvalues, you can argue like this. Suppose that A is diagonalizable. Then there exists invertible matrix M such that inverse of M times A times M is diagonal. But you know that this matrix has the same characteristic polynomial as this matrix. So you know that this matrix has this characteristic polynomial, so its eigenvalues are 0 and 1. So it means all of these guys should be either 0 or 1. Also, you know that there exist 2 linearly independent eigenvectors with eigenvalue 1 in this case. Yeah, because you also at this point we use the fact that geometric multiplicity of similar matrices is the same, and algebraic multiplicity is the same. So only one algebraic multiplicity is the same. So we only use one fact, that similar matrices has the same characteristic polynomial. So this polynomial is a characteristic polynomial of this matrix. It means 2 numbers among diagonal entries are 1. So, but then if you subtract 1 times identity, you get a matrix all consisting of 0, and only in one place you're going to have minus 1. So it's rank 2. So, sorry, rank 1. So its kernel is rank 2 by rank nullity theorem. So this means that geometric multiplicity is 2. But geometric multiplicity of this guy of 1, or for this matrix, we already checked, it's 1. So this is a contradiction. So this is basically the way how you proved that this inequality abstracts you from abstract your matrix to be diagonalizable in this case. Okay, second diagonalization abstraction, which we implicitly mentioned earlier in this criterion, and we also used it already several times in the previous part, so that all roots of your characteristic polynomials must be real for the matrix to be diagonal. But let me just say it slowly, because it's important. So fix n times n matrix, take its characteristic polynomial. By the fundamental theorem of algebra, we know that this polynomial has n complex roots. So it can be decomposed like this: minus 1 to the power of n times lambda minus lambda 1 times lambda minus lambda n. But here, only thing we can say that these numbers are some complex numbers. We don't know that they are real. Yeah. So the complex roots of characteristic polynomial. Some of them may be real. If they're real, we know that these real roots are eigenvalues. So if characteristic polynomial has at least one non-real root, then matrix is not diagonalizable over real numbers. We will see a bit later that this doesn't abstract, of course, diagonalization over complex numbers, but and we saw already examples in the previous part. But over real numbers, end of game. Yeah. Okay, this is example which we already consider in a more general setting. you have this matrix, and you compute its characteristic polynomial, and you see that this characteristic polynomial is lambda square plus 1. So its roots are plus minus I, root of minus 1, no real roots, so it's not diagonalizable. Of course, this is just a rotation by pi over 2 clock counterwise. Yeah, so we already did this case in the previous part. Okay, now what we're gonna do, we're gonna basically briefly state everything we stated for diagonalization of matrices, for real matrices. We just repeat all of this with some corrections, actually with some simplifications for complex matrices. Basically, the motto of this part of the lecture, that everything we did so far for real matrices can be done for complex. So if it looks difficult, it's purely psychological difficulty. This is just because people usually not get used to complex numbers, but in reality, complex numbers are easier than real numbers. Actually, everything we did for real matrices can be done for complex, but its many result becomes simpler, actually much simpler. Okay. So first we fix n times n complex matrix. Complex means all entries now are allowed to be complex numbers. And then by definition, we define the eigenvalue of A is just some complex number lambda, such that AX equal lambda x for some non-zero vector x in n-dimensional complex space. Yeah. So if you have this equality and x is a non-zero vector, again, as for real numbers, it's a crucial point, x cannot be zero. Yeah, then the number lambda is said to be eigenvalue. And this vector x here is said to be eigenvector of A with eigenvalue lambda. Again, this is a complex vector. It can have, in some cases, of course, real entries, because real numbers are complex. Yeah, but not all complex numbers are real. Yeah. Again, by definition, eigenvector not zero. Zero vector is prohibited from being eigenvector. Zero vector is not eigenvector. Okay, and then we can define eigenspace in the same way. Take any complex number lambda. By definition, lambda eigenspace of A is just a kernel of this matrix, A minus lambda I. Yeah, this is a linear subspace, because kernel of any matrix is a linear subspace. Yeah, and of course its dimension is called the geometric multiplicity of lambda, as we will see soon. Okay, we can restate a result about eigenvalues and roots of characteristic polynomial for complex numbers, but it's actually going to be easier. So for real numbers, we know that its eigenvalues are real roots of characteristic polynomial. If you have a matrix with complex entries, then its eigenvalues are all roots of its characteristic polynomial. This can be even considered as a definition of eigenvalue of a matrix. It's of course not exactly the definition, but for example, in my mind, this is almost like definition. Okay, yeah, so lambda is the eigenvalue of A, if and only if determinant of A minus lambda I is 0. Yeah, so this is going to be characteristic polynomial. And this is, of course, the same, but this follows more or less from the definition of eigenvalue if the eigenspace is not zero-dimensional. Yeah. And the characteristic polynomial for complex matrix, of course, is defined in the same way as for real. You take matrix A, consider lambda as a variable, subtract A minus lambda identity, expand, get a formula, simplify, and then you get a polynomial in lambda of degree n. The leading term is, as with real numbers, minus 1 to the power of n. The final term is a determinant of your matrix, yeah, and the term a to an minus 1, determined for coefficient in front of lambda to the power of n minus 1. This is just a trace of the matrix A multiplied by minus 1 to the power of n. Yeah, so we have this equality for characteristic polynomial, it's just -1 to the n, and here we decompose it as a product of polynomial of degree 1, lambda minus lambda 1, lambda minus 2, lambda minus lambda n, and now we can state that these are all eigenvalues of A, all complex eigenvalues of A. Of course, we can say that these are roots of this polynomial, but we already know from this condition that this is the same thing as being eigenvalue. Yeah. So your constant term of your polynomial, characteristic polynomial, is just determinant of your matrix A. And if you substitute lambda equal to 0 here, you see this is just the product of roots of your polynomial. It's a product of eigenvalues. So product of eigenvalues of complex matrix. This is a determinant. Yeah. And as I already mentioned, this coefficient is nothing but the trace of a matrix multiplied by -1 to the power of n. Okay, so again, this is absolutely the same as for real matrices, but a little bit simpler. Why simpler? Because now there's no difference between eigenvalues and roots of characteristic polynomial. It's just the same thing. Okay, good. Next, we can define similar complex matrices. This is just a copy-paste for definition for the real matrices. Two complex matrices said to be similar if they related by this equality. A equal m times b times inverse of m for some invertible complex n times n matrix M. Okay. And we say that matrix is diagonalizable, complex matrix is diagonalizable if and only if it is similar to diagonal complex matrix. Yeah. Again, here you don't assume that, you cannot even assume that this lambda 1, lambda 2, lambda n are real, because everything now is complex. Some of the numbers can be real, but some can be complex. So this is same definition as for the real matrices. Okay, and we repeat proposition which explicitly state how to diagonalize your matrix and when it can be diagonalizable. So if you have n times n complex matrix and you fix some m invertible n times n complex matrix, and you take B to be diagonal complex matrix with entries lambda 1, lambda n, then you write M as a, you denote columns of M by V1, V2, Vn. So V1, V2 up to Vn are columns of matrix M. Then you have this equality, inverse of M times A times M equals diagonal matrix B, if and only if we have this system of equalities. AV1 is lambda 1 times V1, AV2 is lambda 2 times V2, and AVN lambda n times n. So this means that V1 is an eigenvector of A with eigenvalue lambda 1. V2 is an eigenvector of A with eigenvalue lambda 2, and lambda n is an eigenvalue of A, and Vn is corresponding eigenvector. Yeah, this is give you a recipe how to diagonalize matrix A. You just first thing you do, you find eigen values, exactly n, maybe repeated. Then for each eigenvalue, you try to find eigenvectors. And if you have repeated eigenvalues, you have to be sure that these eigenvectors are linear independent. And then you have to be sure that in total you get n linearly independent vectors, because if they're linearly dependent, if lambda v1, v2, vn, if this is your eigenvectors, if they're linearly dependent, they gonna form a matrix M. You can cook up the matrix M in this way, but its inverse not gonna exist. So inverse exists if and only if these vectors linearly independent. Okay, and then you just substitute matrix M in this equality, and you must get B, where B is a diagonal matrix with entries lambda 1, lambda n. These entries are eigenvalues of matrix A, which correspond to the corresponding columns. Corresponding columns are eigenvectors that correspond to this entries lambda 1, lambda n. Okay, the proof is absolutely the same, essentially the same as for real matrices. You just multiply this equality by M, you get equality AM equal MB, and then you just observe that AM is nothing but the matrix AV1, AV2, AVN, where AVI you put as the ith column of the matrix. And when you multiply matrix M times multiply by B, you get a matrix whose columns are just vectors lambda 1 V1, lambda 2 V2, up to lambda n Vn. And then you make them equal, and you get this, because yeah, two matrices are the same if the columns are the same. Okay, this gives you a condition which I implicitly mentioned. Matrix is diagonalizable if and only if n it has n linearly independent eigenvectors. This is just the same as for real matrices, the only difference that here on this slide everything is allowed to be complex. Okay, and this is not obvious, but the proof is absolutely the same, just a copy paste of the proof that we did for real matrices. If matrix A has n distinct eigenvalues, then the corresponding eigenvectors are linearly independent. So in particular, A is diagonalizable. So this gives you the very simple, cheap criterion for diagonalization. Okay, now we can restate this condition in terms of geometric and algebraic multiplicities, but we first have to define them, which can be done absolutely in the same way as for real matrices. There is no difference. The only difference that now entries can be complex. Okay, so by geometric multiplicity of a number, we denote the dimension of the kernel of this matrix. Yeah, and algebraic multiplicity of a number, this is the largest power of lambda minus delta that divides characteristic polynomial. So if algebraic multiplicity is positive, this means delta is just a root of characteristic polynomial. And in this case, we know that this delta must be an eigenvalue, and we know that the matrix A minus delta I should have zero determinant. Then we know by the complex rank nullity theorem that this nullity of this matrix is positive. So if algebraic multiplicity is positive, that geometric multiplicity is positive. But usually geometric multiplicity, not usually, it's always less or equal than algebraic multiplicity, but in some cases it can be smaller. So we always have equality that geometric multiplicity of a number, it's less or equal than algebraic multiplicity. But in some cases, geometric multiplicity can drop, can be smaller. Yeah, and if this happens, this is a problem, and we have this nice criterion for diagonalization, which is the same as for real matrices, but it's simpler. One condition disappears. And this is actually why complex numbers are better than real. You just take all complex eigenvalues of your matrix A, you take matrix A, you take characteristic polynomial, you just list all its roots, lambda 1 up to lambda m. For each root, you compute algebraic multiplicity and geometric multiplicity, and you compare them. Geometric less or equal than algebraic. If we have equality in every case, if geometric multiplicity of every root of characteristic polynomial is the same as algebraic multiplicity, matrix is diagonalizable. If at least in one case this is not correct, if at least in one case geometric multiplicity is less, strictly less than algebraic multiplicity, matrix is not diagonalized. This is very nice criterion. Again, here there are no condition that some roots are real or something, because all roots are complex. Now it's complete equality. In the real case, when we consider real matrices, we have to kind of consider real root and non-real root of a characteristic polynomial separately. Now all of them play the same role in this theorem, that we don't make any distinction who is real, who is not real. All of them lives in one big complex world. Yeah, this is a very nice criterion, and we know how to apply it. Yeah, let's try to apply this criterion in this case. I deliberately consider case 4 by 4, and I will explain why. a bit later in few slides. We consider this matrix and we want to check is it diagonalizable or not. We want also, if it's diagonalizable, we want to diagonalize it. We want to find matrix M such that M inverse A times M is diagonal matrix. This is a very nice complex matrix. It's all its entries are very nice complex numbers. They're also real, but it doesn't stop them from being complex. So this is absolutely okay. Good. So we first compute characteristic polynomial. This is, it takes some time. Of course, I used Python here, so I didn't do it by hands, but it's okay. You can use any computer algebra package. You compute determinant, you get this. Then every computer algebra package, you can use some command to factorize such polynomials. Usually it's just called factor, like in Python or in Maple, you just write down factor this and you get this. And you say, oh, here are the eigenvalues. Nice complex numbers, 1, 2, and 4. And we see that algebraic multiplicity of 1 is 1, algebraic multiplicity of 2 is 1, algebraic multiplicity of 4 is 2. Okay, so if there exists a problem happened here. Because remember, algebraic multiplicity bigger or equal than geometric for eigenvalues. But geometric is always, for eigenvalue, geometric multiplicity is positive. So in this case, for lambda equal to 1, geometric multiplicity is bigger or equal than 1, but it's less than or equal than 1. So it has to be 1. So in this case, my theorem on the previous slide satisfied this condition. Geometric multiplicity equal algebraic. For this root, algebraic multiplicity equal geometric. For this, I don't know. Why? I know that geometric multiplicity is bigger than 0. It's less or equal than 2. So it can be either 1 or 2. If it's 2, we're done. We apply the previous theorem. Fine. We're happy. Matrix is diagonalizable. But if it's 1, we have a problem. Matrix is not diagonalizable. How to check this? By definition, you take matrix 4 times identity, you subtract from A. Basically, this means that you subtract 4 from diagonal. So you're going to have the same matrix, but here you're going to have 4, here minus 3, here minus 1, and here minus 2. Okay, it's 4 by 4 matrix. You have to find its kernel. Well, to be precise, you don't even need to find its kernel. You need to find the dimension of the kernel. You need to find the rank. So rank of your matrix going to be less than 4 by definition. It must drop because determinant of the matrix A minus 4i going to be 0. So rank drops. How it drops, we don't know. If it drops by 1, it means the kernel is 1. So rank by rank nullity theorem, dimension of the kernel space, it's exactly what we're looking for, geometric multiplicity of 4. The dimension of the kernel space of A minus lambda I is 4 minus rank of A. So rank of A may be 3, maybe 2. One can actually show that it cannot be less than 2. Why? Because in this case, geometric multiplicity is going to be 3, but we know geometric multiplicity does not exceed algebraic multiplicity. So rank of matrix A minus 4i can be either 2 or 3. If it's 2, we're done. It's diagonalizable. If it's 3, we have a problem. It's not diagonalizable. Let's compute. Yeah. Okay. So we compute that actually turn out that all eigenspaces are one-dimensional. So rank of this matrix A minus 4i drops by 1 from 4 to 3. So by rank nullity theorem, dimension of the kernel, this is dimension of the kernel A minus 4i, is actually 1. Okay, matrix is not diagonalizable. Okay, so this can be considered as an end of game, but this we can try to fight a little bit more. We can say, okay, why this matrix is not diagonalizable? This matrix is not diagonalizable because we cannot find 4 linearly independent eigenvalues. But we can actually find 3 we can, we know that this kernel is one-dimensional, this kernel is one-dimensional, this kernel is one-dimensional. So it means we can take basis of each of this kernel. In this case, basis of this kernel is just this vector v1. Basis of this kernel is this vector 1 minus 1, 0, 2. And here, I have basis given by this vector. These three vectors are, by definition, eigenvalues of my matrix A with eigenvectors of my matrix A with eigenvalues 1, 2, and 4 respectively. So the problem for diagonalization is that for eigenvalue 4, I couldn't find the second vector. I need another eigenvector with eigenvalue 4, linearly independent with V3. But I cannot do this because all of these eigenvectors, they live in this space, which is one-dimensional. So any two of them going to be basically scalar multiple of this vector. Okay, so we almost succeed. We just missing one vector. And then we can play some game. Let's just play some game. We say, maybe we can just put here some arbitrary vector and see what happens. Yeah. Okay, so I just took vector v4, just arbitrary vector v4. I know that I want v4 to be eigenvector, and I know that it should be with some eigenvalue 4, but I cannot find it. So I just said, okay, let's just take any vector. Why? I want still to repeat my diagonalization process. I know that I'm not going to succeed, but again, hope dies last. Yeah, so maybe who knows? Maybe there's going to be a miracle. Maybe the theorem was wrong, and I'm going to diagonalize my matrix. Of course, it's not going to happen. Miracles do not happen, but still I can try. So I took this vector v4, put some a, b, c, d, some numbers. I find them later, and I want use this basis v1, v2, v3, v4 to form this matrix M and to run diagonalization process. Even if I know that I'm not going to succeed, I'm not going to diagonalize my matrix. Okay, maybe it's a good good attempt, but first I need to check that they're linearly independent, because otherwise, of course, my matrix M composed of these vectors v1, v2, v3, v4 is not going to have inverse. So how to check when they're linearly independent? The simplest condition I know is just to compute determinant. You have this matrix, this is vector v1, this vector v2, v3, v4, and you just compute determinant. This is not so hard. Yeah, you compute determinant and you get this number. Yeah, so if I know that a plus 2b is not 0, then I know for sure that this matrix is invertible, because we have criterion matrix is invertible if and only if determinant is not 0. Okay, suppose this is the case. Let me play more. I just use my pattern for diagonalization. I write down inverse of M times A times M, and I want here to get diagonal matrix. I know that this is not going to happen. But what I'm going to get here? I'm going to get here almost diagonal matrix. It's going to be almost diagonal here. And basically, if you think about this, this partial proof of my proposition, of my theorem, which I mentioned in the explicit diagonalization, partial proof going to work. It's going to work for the first 3 columns of the matrix M. It's not going to work for the last column. Yeah, so here I'm going to have exactly what I want, parts of diagonal matrix. There's a problem only with the 4th column. 4th column, I get some garbage, yeah, like this. And surprisingly, this entry going to be 4, which is easy to see why, because we know these 2 matrices are similar. A and this matrix is similar. So this matrix must have the same eigenvalues of A with the same geometric multiplicity, the same algebraic multiplicities, but we already found them. And this is upper triangular matrix, so its eigenvalues is 1, 2, for and this diagonal entry, so it has to be 4. Okay, so this is basically this equality shows me that if I fail to diagonalize, I still can fight a bit to do something, and maybe I can, if I cannot diagonalize matrix, maybe I can just simplify it as much as possible. The simplest possible shape of a matrix is diagonal, but I cannot do it here. I cannot get diagonal matrix here. So maybe I can get something close to diagonal. I already get something close to diagonal. This part, perfectly, it's just perfect. It looks like diagonal to me. The problem with this part, ideally, I want to kill this term, and this term. I want to make them 0, but I cannot, because if I can, my matrix A would be diagonalizable, but it is not. So then I say, okay, maybe I just can kill as many terms here as I wish. So, okay, the simplest option going to be make this guy to be 0, this guy to be 0. I cannot then make this guy to be 0, but let's make it to be any number which is as simple as 0, so but not 0. So I should be 1, yeah, because 1 is a very simple number. So I basically want to solve this system of equation. This is 0, this is 0, and this is 1. Yeah, it's not hard. It's just 3 ABCD, 4 unknowns, 3 equations. We're not sure a priori that we're going to have solution because it's not homogeneous equation, but we do have solutions, yeah. And we actually have infinitely many solutions. And we actually know from general results mentioned in the previous lecture that in this case, either we have no solutions or we have infinitely many, yeah, because we have 4 variables and just 3 equations. Yeah, but we take one solution, yeah, and you get matrix like this, but here you have 0, 0, 1. This matrix has a name. This is a special case of what is called Jordan normal form of our matrix A. This is beyond this course, but I think it should be part of this course, but unfortunately we don't have time. This is not part of the book, as far as I remember. Maybe it's mentioned in the book, but it goes without proof. This is a very nice result in algebra, which is going to be covered in a different course. I think it's covered in honors algebra, so you're probably going to learn the theorem next year. But I think it's a nice way to show you that this Jordan normal form, it's a natural thing. It's just next step to a diagonalization. You try to diagonalize, you fail, and you do as much as you can, and you get something like this. Yeah. Okay. So this is way beyond the topic of this course, but the scope of this course. But let me just briefly mention what are these Jordan normal forms for 2x2, 3x3, and 4x4 matrices. This is basically something like diagonal matrices, but not diagonal, close to them. So basically, Jordan normal form and theorem about Jordan normal form says for 2x2 matrices, if you have 2x2 matrices, that we know 2x2 matrices can be diagonalizable, can be non-diagonalizable. So if they're diagonalizable, then they're similar to diagonal matrix. If they're non-diagonalizable, they're similar to matrix which is very close to diagonal, basically this form. So we have 2 choices. If A is diagonalizable, it's similar to diagonal. If A is not diagonalizable, you can prove that it's similar to matrix of this shape. Why? Okay, just think about this. Okay, let me give you a sketch of the proof. If you first compute eigenvalues, you find the roots of characteristic polynomial. If the roots are different, it's diagonal, you get this, end of game. If roots are the same, we have one root, then you always have one eigenvector, for sure, almost by definition, actually by definition, yeah. You take one eigenvector, and the second vector, you want to find the basis of your 2-dimensional space. Ideally, it should be consisting of 2 eigenvectors, linear independent, but you cannot if it's not diagonalizable. Or maybe it's diagonalizable, then you can. Then you, in this case, with lambda 1 equals to lambda 2. But if it's not diagonalizable, you have one eigenvector, and for the second vector of your basis of your vector space, you just put some vector with arbitrary coefficients like we did in the previous case. And then you play, and then you must get upper triangular matrix by definition. So you're going to have lambda 1 here, 0 here, and you get something here, some garbage, you don't know. Not necessarily 1. But then you play a little bit with your second vector like we did in the previous case, and you can show that you can make it to be 1. Okay. And this is a sketch. Strong advice, if you want to have fun, just prove this yourself. 2 by 2, this is not complicated. This is okay. Okay, 3 by 3, we have more choices. We can try to diagonalize my matrix. You can find a similar matrix which is diagonal. If you succeed, you get diagonal. If you not succeed, if A is not diagonalizable, you can have one of these two cases. Either this or this. This is basically as simple as you can get. Yeah. And for 4 by 4, you have more cases, and these blocks, how you split your matrix, they're usually called Jordan cells or something like that. It doesn't matter, but it basically shows you the simplest possible matrices that are similar to your matrix. Yeah, the simplest possible, of course, is diagonal, but if you're unsuccessful in diagonalization, you can get something like this. In 4 by 4 case, something like this, in 3 by 3, and something like this in 2 by 2. Okay, and let me more or less complete this part by one very important result, which you will see in other courses. But we need this result next week for real matrices. But the proof, surprisingly, involves complex matrices. And we cannot prove it without using complex matrices. So let me state it. You fix n times n complex matrix, and you denote by A bar a complex conjugate of the matrix A. It's basically the same matrix A, but all entries of the matrix A, you take a complex conjugate. So let me recall, if complex conjugate of complex numbers A plus BI is a complex number A minus BI. Okay, good. So if you forget about this, please take a look at the lecture notes. What are complex numbers and what are complex conjugate? Okay, so now we suppose very interesting condition. We suppose that my matrix A satisfies this equality. If you first transpose it, flip around diagonal, and then you take a complex conjugate, or other way around, it doesn't matter, they commute. Then you get back my matrix A. Look, this is a special case of symmetric matrix. If A is symmetric matrix, with real entries, if A is a real, if all entries of A are real, this is not prohibited because real numbers are complex. If A is a real matrix, then complex conjugation of a real number is same real number. So then complex conjugation of A is just A. Then this is just definition of a symmetric matrix. So matrices with such properties usually called Hermitian matrices. They named after French mathematician Paul Charles Hermite. And this can, for if matrix A is real, this is just symmetric matrices. Anyway, so we take a matrix N with this condition, and then this lemma said that all eigenvalues of A are real. This is a fantastic result, and if you think about this, the corollary of this result, that symmetric matrices, all eigenvalues of symmetric matrices are real, which is absolutely not obvious. Just my advice, prove it for 2 by 2 matrix. Take a 2 by 2 symmetric matrix, A, B, B, C. You got quadratic polynomial. Prove that it's actually, all its roots are real, if A, B, and C are real numbers. This is not obvious, but of course you can use a formula for quadratic, and you get discriminant is positive, and end of game. Try to do the same with 3 by 3. Take 3 by 3 real symmetric matrix. You want to prove that all its eigenvalues are real. Okay, I'm a little bit abuse notation here. When I say all eigenvalues are real, I mean that complex eigenvalues. It means roots of characteristic polynomial. So because on this slide, I assume all matrices are complex, even if they have real entries. So again, let me maybe restate it to be more clear. Take 3 by 3 real symmetric matrix. Compute its characteristic polynomial. Then all its roots must be real. This is absolutely non-trivial because you know that one root of cubic polynomial is real for sure. Why? There are other two roots. You don't know. It's not obvious, but it follows from this lemma about complex matrices. Okay, let me show you how to prove it. The proof is surprisingly simple and actually looks like a miracle. Okay, here is the proof. So you take an eigenvalue. Again, this is a complex number. You want to prove that it's real. Again, real numbers are complex. Complex, not always real. They can be. So we took its eigenvalue. It's a root of a characteristic polynomial of matrix A. Okay, we know that there exists eigenvector with eigenvalue lambda. It's a complex eigenvector, but we know for sure it exists. Yeah, because my matrix A minus lambda I has determinant 0. So by rank nullity theorem applied to complex numbers, I know that the kernel is positive dimensional. So I took any non-zero vector in the kernel. This is my vector X. Okay, and now I start playing with this. Playing like this. I write this product. This is the central part. This or all that, but maybe that's. Let's look here. I take matrix A, multiply by vector X. I can do this. And then on the left, I multiply by the conjugate of vector X transpose. So this is basically a row. We deal with vectors like columns, they're vertical. But when you take vector transpose, this is basically means it becomes a horizontal, yeah. So this is sort of dot product. Yeah, this looks like dot product, but it's called a Hermitian product. You will learn it later. Yeah, and conjugation means you conjugate every entry of vector X. So, okay, you get this guy. And now you just slowly play with this number. This is a number. A times X is going to be a vector. And you have vector multiplied by the transpose of a vector. So as a result, this is a number. This is a number. Let's compute this number in two different ways. First, you just use the fact that lambda is an eigenvalue. So A and X is an eigenvector. AX is just lambda X. So you get this. But lambda is just a number. When you multiply vector by a number and multiply it by another vector, you can just put lambda outside of the product. So this is the same as this. Lambda X bar transpose X. Okay, you get this guy. But on the other hand, we can rewrite this equality in this way. You actually can put A and multiply, you can basically replace A by A conjugate transpose, A bar transpose, by the assumption, because we know by assumption that these two matrices are the same. You just rewrite this product as this. And then we use the fact that product of matrices are associative. Of course, I can multiply this A bar transpose by A, but now I want to multiply it not by X on the right, but by X bar transposed on the left. So I first multiply these two guys and then multiply by X. But with one of the properties of transpose of matrices is transpose of the product. It's product of transpose taken in the opposite way. So this product is just multiplication A bar transpose X bar, A bar times X bar transpose. Again, transpose of the product of two matrices, it's a product of their transposes taken in the opposite way. Okay? So you have this. But then you say, okay, when you multiply matrices, or your matrix is a vector, or you take the conjugate, this is sort of, doesn't matter in which order you do. First, you can take matrix A, vector X, takes the conjugate, multiply, or you first take matrix A, vector X, multiply, take the conjugate. This follows from the following properties of complex numbers. Complex conjugate of product of two complex numbers, it's a product of complex conjugates of these numbers. Basically, A bar times B bar is equals to A times B, and then you take a complex conjugate of the product. This is property which you can check by yourself for any two complex numbers. This is quite straightforward. Or you can look at the lecture notes, or you can, if you, for example, take an accelerated proofs and problem solving, you probably already covered this in this course. Okay, anyway, we have this equal to this. Okay, but now you say, okay, wait, you can say A times X, this is nothing but lambda X, yeah, because X is an eigenvector with eigenvalue lambda. So you replace this guy by this guy, and then you use the same property again. If you multiply a number by a vector and then you take a transpose, it's the same as to multiply they transposes. Yeah. So you replace this by this. And now you compare the left side and the right hand side, and you see that they are almost identical. The only difference that here on the right hand side you have lambda, on the left hand side you have lambda bar, complex conjugate of lambda. So now, if I can cancel this term, if I can divide this term, then I get lambda equal to lambda bar. But by definition, complex number equal to its complex conjugate if and only if imaginary part is 0, if and only if it's a real number. Again, if you have a complex number a plus bi, its complex conjugate a minus bi. They equal if and only if b is 0. It means that this is a real number. It has no imaginary part. Yeah. So exactly what we want to prove. So the last step of the proof, we just need to explain why this x bar transpose times x is a non-negative number, so we can divide by it. It's a number. We only need to know it's not. We only need to know it. Sorry, not 0. We only need to know it's not 0, so we can divide by it. But we can actually write it explicitly. If your vector x is x1, x2, x3 up to xn, its coordinate, then x bar is vector x1 bar, x2 bar, xn bar. So basically the complex conjugate of this entries of vector x. But then when you transpose it and you multiply, what you get as a product is a sum of x1 times x1 bar plus x2 times x2 bar, blah, 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 up to xn times xn bar. But if you have complex number, if you multiply it by its complex conjugate, you get what is called the modulus of complex numbers squared. So basically, if you take a plus bi times a minus bi, you get a squared plus b squared. So this is a positive number, positive real number, unless it's a 0 number. So if at least one entry of vector x is not 0, this is a positive real number. But vector x is not 0 by definition, because it's an eigenvector. So this is a positive real number. And this is the same number. So you can just cancel and you get what we want here. And we have a very powerful corollary, which I mentioned already. Yeah, so for example, you take any, just conclusion, every real symmetric matrix has at least one real eigenvalue. And we actually know that it has all its roots of characteristic polynomial are real. All. So for example, for 3 by 3, we know that at least if you have a real matrix, 3 by 3 real matrix, we know that at least one real, it has at least one real eigenvalue by intermediate value theorem. But if it's symmetric, we know that all roots of characteristic polynomials are real. Of course, they may coincide. So to be precise, you cannot say that it has exactly n different eigenvalues. because some of them may coincide. So, but we know for sure that we have all roots of characteristic polynomials are real. Counted with multiplicity, we have n real root eigenvalues. Yeah, okay. We will use this next week. This is very powerful result, and actually we will improve it. You will see, we will prove a stronger statement. Okay, let me stop the recording.